For those of you who are coming here for the first time, welcome to the FHE.org meetup. So FHE.org is a community around homomorphic encryption, where we talk about everything from engineering to science to potential applications of homomorphic encryption. We have those monthly meetups where people present the work that they've been doing. And we also have, of course, the Discord server where you can talk about homomorphic encryption, and we also provide support for some of the different frameworks. When I say we, I mean the community, of course. So my name is Rand. I'm the CEO of a company called Zama, where we have been working on the concrete framework for homomorphic encryption. If you guys are interested in the TFHE scheme specifically, you'll find a lot of stuff coming out of our team on that. But this is not about Zama. This is more about a community in general. So this is completely independent. So today we're going to have a talk about private information retrieval from Mohammed, who's a PhD student at Urbana, Champaign in Illinois. So Mohammed, I'll let you introduce yourself. And again, welcome everyone. Looking forward to hear what you have to say, Mohammed.
Great, thank you. Let me just share my screen. Can you all see my screen?
Yep.
Cool. Okay, so thanks for introducing. My name is Mohammed Harris, and I'm a PhD student in University of Illinois, Urbana, Champaign. And I work in applied cryptography. Specifically, from last few years, I have been working on using homomorphic encryption to improve primitives like private information retrieval, private site intersection, Oram. So today I'm going to talk about single server private information retrieval using homomorphic encryption. Private information retrieval, or PIR, was proposed in 1995. This is a basic primitive, cryptographic primitive, which allowed the user to fetch a record from a database on the server without revealing to server any information about which record has been retrieved. So database is hosted on the server, and the clients can interact with the server to fetch a record. PIR has been used in many applications. They have been recently, from the system research point of view, there have been many applications proposed for PIR. They include media streaming, messaging, password checking, safe browsing, advertisement navigation, and so on. At a high level, PIR has two requirements. First is correctness, which means that with high probability, client learns the record of interest. And second is privacy, that the server learns nothing about the client's input. There are two categories of PIR constructions, one that involves multiple non-colluding servers. And in this setting, the server database is replicated on each server. And the privacy only holds if at least one of the server is honest or do not collude with the adversary. I would also say that these schemes are computationally very efficient than their single server counterpart. In this talk, however, I will only consider the single server PIR schemes. These schemes are usually based on some cryptographic assumption and therefore only provides computational security. Okay, before going into more in depth with PIR, I would like to give an overview of some of the similar primitives. These primitives have been used a lot in FHE community recently. FHE has improved these primitives a lot more. So, and they are kind of similar, but they have their own differences. So all of these primitives hide client's query and access pattern. So this is their similarity. As you can see here, that the database server, the database at the server is plaintext is for all of these primitives except Oram. So in Oram, the server cannot see the database. Similarly, Oram requires a client to have this private state, due to which multiple clients cannot interact with the Oram server directly. We need some special mechanism. However, all the other primitives, PIR, OT, and PSI, do not require the client to have any kind of state, and they can just, therefore multiple clients can interact with the same server without any additional computation. The client input in all of these schemes are indexes except PSI, where the client input are the set of records. And Oram allows the client to do read and write, while OT and PIR only allow the client to do reads. And PSI, of course, allows the client to compare and compute equality, to check equality. Okay, so because of the similarities of these primitives, they can be used to create constructions for each other also. For example, OT has been extensively used in PSI to create very efficient PSI schemes. And similarly, PIR can be used to create a PSI. Also, there is a variant of PSI called symmetric PIR, variant of PIR called symmetric PIR. And that variant can be used directly to create a computational efficient OT schemes. So this is overall of these schemes. Okay, the efficiency in PIR, back to PIR now, is measured using 3 key metrics. First is the client request size, that how much data client is sending to the server. Second is server computation, that how much compute server has to perform per client query. And third is the response overhead. Sorry, there's a typo here. It should be response overhead, response size, that how much data server returns to the client per query. There is a trivial PIR scheme in which the client does not have to send anything to the server, and server just transfers the whole data base back to the client. Note that, sorry, I forgot to highlight in the previous here that in PIR, server does not, there is no privacy for a server database. So as you can see here, that there is no privacy in the server database. So server database can be considered as public. And that's why we have this trivial PIR scheme where the server can just send the whole database back to the client, and client can just get the entry directly from that database. So this is perfectly accurate PIR scheme. However, this PIR scheme has a very high response size, although it does not have any request size, any computation, but still the response overhead is quite big. You can see it's a linear, like for every query you're sending the whole database, which is not ideal for many applications. So the additional goal now, or the additional requirement of PIR scheme is that the computation should be less than the size of the server database. So that's where all these advanced or newer PIR protocols lie. So this is the outline for my rest of my talk. I'm first going to talk about state-of-the-art single server PIR schemes, which include XPIR and SealPIR and our recent work, OnionPIR. And then I will discuss some of the two techniques which improve the PIR computation. This includes batch PIR and stateful PIR. So let's talk about the state-of-the-art single server PIR scheme. Okay, state-of-the-art single server PIR schemes are built on somewhat homomorphic encryptions, or we can call them SHE. These encryption schemes actually support limited number of homomorphic encryption, homomorphic operations directly on a ciphertext. Specifically, most of the recent schemes are using the SHE, most of the recent protocols using the SHE scheme, which are based on learning with error assumption. So just a little bit of background on how the learning RLWE ciphertext looks like. In RLWE ciphertext, the higher order bits encodes the messages, and the lower order bits encodes a noise, and noise is added for the security of these schemes. So we have to add noise. The important metric for all of the protocols which are built on top of these schemes are called expansion factor, which is nothing more than the size of the ciphertext divided by the size of the plain text. So it gives us how much overhead we are paying in terms of communication just for sending and receiving some data. As I said, that SHE schemes allows performing operations on the ciphertext. The problem is after each operation, the noise in the resulting ciphertext increases. And if the noise increases too much, that then the ciphertext can become damaged or inaccurate. So if you try to decrypt that ciphertext, the result will be inaccurate. That's why most of these schemes only support limited number of ciphertext, and every protocol designer actually try to pick parameters such that the noise never becomes too high. Okay, so one thing about these operations is that in SHE, ciphertext addition is a good operation. Like by good, I mean that the noise in the output ciphertext only linearly increases. However, the multiplications increases the noise by the multiplicative factor. Especially, we want to avoid homomorphic multiplications because that adds a lot more noise. And these are actually, homomorphic multiplications are actually the way we try to measure the efficiency of the protocol. So we measure that how much multiplicative depth this particular protocol has. Okay, now the basic PIR. In the basic PIR scheme, database is represented just like a plain text array. And the client request consists of a query vector, which is 1 at the desired index and 0 otherwise. Since the query vector is private, so client cannot just directly send this query vector to the server. So what client does is it encrypts the query vector, component-wise encrypt the query vector into using RLW ciphertext, and the server just compute a dot product between ciphertext and the plain text. And the output is just a single ciphertext. This scheme is completely fine, but note that now the request size is too large. So in trivial PIR, response overhead size was way too big. And now the request size is equal to the size of the database. So we are back to the same thing. In order to reduce the request size, 2 approaches have been proposed by the recent schemes. First approach is called Hierarchical PIR. This approach has been used by XPIR, SealPIR, and even our work, which is OnionPIR. And then second approach is called request compression. This is a new thing which was proposed by SealPIR. So in hierarchical PIR, basically the database is represented as d-dimensional matrix. The side effect of this thing is that this reduces the request size. So the request now consists of d query vectors, each of size dth root of n. However, the negative thing about this scheme is that this also increases the multiplicative depth to d, which means we will have a lot more noise and we will have to pick higher FHE parameters, which will increase the computational overhead. So what previous schemes have done, they come up with this interesting trade-off. So they fix the d to be equal to 2, and the database is now represented just as a matrix. And the client request now consists of 2 query vectors, each of size square root of n. So rather than having more dimensions and have higher multiplicative, that they are stuck with 2 dimensions only. Okay, so ideally now, so that's hierarchical PIR, and now we are going to talk about request compression. So ideally what we want the client to be able to send the encryption of desired index, and the server should be able to expand it into a query vector, right? And we can perfectly do it using FHE, but the problem is that FHE, computing that function will require, will have a very high noise multiplicative depth, due to which there will be high noise growth, and we will need higher FHE parameters. In fact, so high that it could be, that particular expand operation could become the compute bottleneck for the whole protocol. So we want to avoid that. Okay, so let me just go back and look at the RLWE ciphertext again. So actually the plain text is a polynomial where each coefficient of this polynomial can represent a data. So when I said previously, I glossed over it, but it is actually a polynomial. Previous work have proposed a substitute operation. This operation takes encrypted RLWE ciphertext and a power and raise the encrypted plain text polynomial to that power. This operation has a very less noise growth, much less than homomorphic multiplication. It turns out that we can combine homomorphic addition, ciphertext plain text multiplication, and substitute operation to implement an expand function. In other words, we do not need homomorphic multiplication, which we wanted to anyway avoid because of high noise growth. So what expand function actually do is it takes a RLWE ciphertext as input and expand it into an array where each coefficient of input polynomial shifts to the constant term of the output polynomial. So for example, here 2 in the second ciphertext, 2 shifts to the constant term of the output polynomial. So now in SealPIR combine both of these techniques. They keep the hierarchical PIR with d equal to 2 and ciphertext expansion, this expand function. And by combining these two techniques, their request size is actually only 2 ciphertexts. So they pack each query vector into a single ciphertext. So since there are 2 query vectors, so the total request size is only 2 ciphertexts, which is pretty good actually. And now their computation is just after expansion, the server performs ciphertext plaintext, perform dot product using ciphertext plaintext multiplication. And in the second dimension, they need this homomorphic multiplication. However, they wanted to still avoid this homomorphic multiplication to keep the expansion factor smaller. So because of which they have a high response. So now I'm going to discuss why these schemes. So the request is totally fine. As I said, it's 2 ciphertexts, but these schemes, SealPIR has a high response overhead. And here I would give a little bit intuition on why this response overhead is too high. First of all, they have a higher expansion factor. So their expansion factor is 10x, which is the main reason being because in the first dimension, they have to do this ciphertext plaintext multiplication, which adds a lot more noise as we see. So that's why they have to keep the expansion factors higher. And secondly, they avoid this, in the second dimension, they avoid the homomorphic multiplication to keep the noise in control, due to which their overall response overhead becomes 100x, which is, it's actually f squared. So their f is 10, so it becomes 100x overall response overhead. Okay, so how did they avoid the ciphertext multiplication in the second dimension? So what they do, instead of directly note that after the first dimension, computation of the first dimension, the second dimension consists of set of ciphertext at the server. So what these schemes do, they split this ciphertext into smaller chunks, the ciphertext which is a result of the first dimension, and then use them as just as a plaintext ciphertext, plaintext in the corresponding dot product. So in other words, you can think of it that after another way to look at the previous slide is that after splitting, the intermediate database can be represented as a matrix with F columns. The server compute now is a dot product between the second query vector and the columns of this matrix. The output now consists of F ciphertext, which results in an overall 100x overhead. So in summary, they just avoid the, in order to avoid the homomorphic multiplication, they have this, they pay for higher response overhead. Okay. So now I will talk about how we get away with this high response overhead in our work. It's called OnionPIR. So the key building block there is this special operation with the low noise. This operation is called external product. Basically, it multiplies 2 ciphertexts from different schemes. One is from RLWE ciphertext and another is RGSW ciphertext. And the output will also be RLWE ciphertext. The key advantage of this operation is that if the plaintext encrypted in RGSW ciphertext is binary, then the output noise is additive, right? So, and also note that the noise does not depend on the plaintext, which is encrypted in the input RLWE ciphertext. So in other words, if RGSW only encrypts zeros and ones, the output noise after multiplication is additive. So, okay, now, so we have this operation. So the basic, a simple approach could be to just use RGSW ciphertext for client query vectors and replace all the multiplication operation with external products, right? This approach already has a low noise growth, which allow us to have expansion factor of 4.2. Note now that we also do not require a ciphertext splitting in the second dimension. In fact, with this approach, we can use hierarchical PIR approach to full extent and represent the database as a high dimensional queue, such that the client request will now consist of logarithmic number of query bits. Also note that good thing is that the output of this scheme will be just a single ciphertext, RLWE ciphertext, because we are just going to replace everything with the external product. However, there is a problem. Each external product is around 5x more expensive than our homomorphic multiplication using only RLWE. So the basic scheme will be around 5x costly in computation, right? So how we get away with that? So we solved the issue of response, but now we have an issue of compute. So we improved the response, but we increased the compute by 5x. So the way we solve it at OnionPIR is by having this clever trick where we note that the first dimension is a ciphertext plain text multiplication. So we keep the ciphertext plain text multiplication using RLWE ciphertext. And we increase the size of the first dimension quite a lot so that the first dimension becomes the compute overhead. And then in the subsequent dimension, for the higher dimension, we use external products only. So for the first dimension, we use RLWE multiplication, and then the subsequent dimensions, we use the external products only, which gives us additive noise growth. So the overall effect is that the computation is dominated now by the first dimension, which is similar in OnionPIR and SealPIR. Therefore, both schemes have a comparable computational cost. However, the response overhead of OnionPIR is much smaller. So I'm not going to discuss today, but in paper, we also discuss few more things. Specifically, there is still a high noise growth in a multiplication of a first dimension. And since we have such a small expansion factor, so we have a low noise budget. So unlike SealPIR, which has a higher expansion factor, we cannot handle that big of a noise growth. But in the paper, we explain how we handle that noise growth. So I would, and also we also improve the query packing. So now we only have to send a single ciphertext. So the client will only going to send one ciphertext to the server, and servers will be able to expand it into RLWE query vectors and RGSW query vectors. So these are some of the results, how the state of the art looks like. So as you can see that these results are for a 30 kilobyte, where each plain text data is of size 30 kilobyte. You can see that the response overhead of OnionPIR is much better than SealPIR. SealPIR has around like 3 megabytes of response overhead response size, and while OnionPIR only has 128 kilobyte. Also note that the total computational cost between OnionPIR and SealPIR does not change much. And also in terms of server cost, OnionPIR is better until for a smaller database, OnionPIR is better. But for the bigger database, they are almost, OnionPIR and SealPIR is almost similar. And it is mainly because for a larger database, actually computes become the financial bottleneck. Monetary bottleneck. So reducing response does not too much affect there. Okay. There is another concurrent work from Google called MulPIR. They have a little bit different approach. Rather than doing this mix of RLWE and RGSW ciphertext, they actually try to pick higher FHE parameters and do not avoid the homomorphic multiplication in the second dimension. So they take SealPIR, they pick the higher FHE parameters, and they do not split the ciphertext in the second dimension. Still, they're overall, so these are just estimated results, but still their request size in all the three main parameters, they are performing worse than OnionPIR. So for example, their request size is 119 kilobyte, and they in fact further increase the computational overhead, which is very high already in any scheme, in any PIR scheme. So what is the takeaway from until now? The takeaway is that all these PIR schemes have decent request and response sizes now, but the computation is still heavy. And this computation is inherent because server has to touch every end record, otherwise it will rule out the untouched record. So high computation is side effect of client privacy. Okay, so this is half of my talk. Do we have any questions at the moment, or should we take question at the end?
Actually, we have quite a few questions in the chat. I think, guys, it's more friendly if you ask the questions directly. So those of you who ask questions in the chat, maybe you can just unmute yourself and ask them to Muhammad directly, and we can answer, and then we can continue to the other half of the talk.
I did ask a question, but then I answered it for myself, so I don't need to ask my question.
Okay, Nigel. So I think we had a few more questions. Liwei or Azul, you were asking things as well? Okay, I guess Mohammed, I guess you can continue your talk for now then.
I do have a question.
Okay, go ahead.
Which is just on your last comment. You said that these PIR schemes, maybe you're going to address this later. These PIR schemes are inherently slow because the server has to touch everything. Yeah.
Yeah.
But in ORAM, it doesn't.
Yeah.
So in ORAM, you kind of hide the access pattern by kind of randomly touching stuff. Is there kind of can you kind of take that kind of philosophy from ORAM to make PIR more efficient?
Yeah, that's a very good question, actually. Let me go back to my, sorry, problem is, as I showed in this slide, the ORAM, the database is encrypted by the client. So client encrypts the database and send it to the server.
Yeah, good point. Yeah.
So there is a IND-CPA there, right? So the server do not see which entries have been touched.
Yeah.
And you can maintain that, okay, I touched this logarithmic number of entries in each access. Server has no idea what those entries are. But you cannot do it in PIR. Because server is looking at each and every entry. It knows which are the dummy entries and which are the real entries.
Yeah, but you could kind of give it, you could say, please touch these 1,000 entries, but it doesn't know which one is the one you actually get. It just knows that it's one of these 1,000, which is, I mean, it's not perfect security, but it is.
So server knows which are the 1,000 entries or not?
Yeah. So you could kind of say, here are the 1,000 I'm touching. So it would kind of, it would give you some, it would be a trade-off between security and efficiency is kind of.
Yeah, you can do that, but then you have to quantify the leakage because of that.
Yeah, like, apparently Mark Olivier says there is something called k-anonymity PIR. Is that true?
I don't think so. I mean, it's just that what you said made me think of anonymous PIR.
Okay, so we just invented a new topic.
I think the issue is that we want to keep the client as stateless. So client should not have any kind of state. If client does not have a state, then client makes these random queries, right? And it can make this subset of random queries, which server will know. But then we have to carefully quantify that what kind of information is leaked to the server.
Yeah.
It will be definitely a weaker form of.
Yeah. Okay, thank you very much. Thank you.
And I'm going to talk about something similar actually in the later part of the talk.
Okay, I suggest we move to the later part of the talk, and then we can take more questions once we're done.
All right, okay. So let's try to see how can we improve PIR computation. One method which has been proposed in 2004, it's called batch PIR. Now the client wants to retrieve a batch of entries. So let's say the size of the batch is B rather than a single entry. The goal is that the client should be able to retrieve all the entries in a server computation, which is sublinear in B into N, where B is the size of the batch and N is the size of the server database. So the client this is a very simple form of batch PIR. What they do is the client and server randomly partitions the server data into B buckets, right? After that, with the standard ball and pins argument, we can argue that the maximum number of client's entry, if assuming that the client entries are arbitrary, maximum number of client entries that fall in each bucket is logarithmic in B. So the client and server can now run multiple PIR per bucket. So note that since client wants to hide from the server distribution of its input into buckets, therefore client will always have to make logarithmic number of queries per bucket. And client can do it by using dummy queries. So even if the certain bucket has less number of client entries, it has to still do logarithmic number of client entries. In total, the client and server runs logarithmic number of PIR queries on B buckets, each of size n over B. Okay. So this scheme has a server compute of order of n log B. However, the more recent scheme, which is part of SealPIR, the server computation can be reduced to linear. So it's order of n, and the fact, and even the constant factor there is just 3. However, the problem with the batch PIR is that the client must know all the indexes at the time of making theory. So it's only suitable for very specific kind of applications. But we want to be able to make adaptive queries. And by adaptive here, I mean that the client should be able to pick queries one by one. And for that, there is a recent work. This is a very recent approach to reduce computation in PIR. It's called Stateful PIR. You can think although not very correctly, but one way to think of it is more like Oram, that now client has a state, but still the server database is unencrypted, and server does not have to perform a different computation for each client. So that server database does not changes. So there are 2 works in, first it was proposed by a work from Google called PSIR in 2018, and then our recent work has improved this scheme. So the overall idea is that now to reduce the high computation of PIR, in stateful variant of PIR, the high level, the client fetches some state from the server, then in the offline phase. Then in the online phase, the client can utilize the state to make certain number of cheaper online queries. So this, for the people working in MPC, this would also remind them of like offline phase, offline MPC or pre-processed MPC. So in the previous scheme, the client hint is actually consists of subset sums. That's it. So the state, for example, for a given database, the client state is 3 subset sums, right? Now suppose that client wants to fetch a record M3, which is hosted on the server, from the database hosted on the server. Client picks a state or a subset that does not contain M3. For in this case, this blue one is the one the client is going to pick. Now, sorry, the client will pick the part, and the client then asks the server to arrange the database in a pseudo-random matrix. And in the paper, it has been shown that client can just ask the server to do it very cheaply just using PRFs. Okay, such that this pseudo-random matrix, in this pseudo-random matrix, one row is equal to the concatenation of entries in the picked subset and the desired element. For example, one of the rows should be equal to M3, M2, M5. Note that from the server's perspective, this arrangement is completely random, so it does not learn any information about the row. Sorry, I forgot to mention that server doesn't know what client state is. The server then column-wise add the database. Note that this addition reduces the effective size of the database. For example, the database for us in this example reduces from 9 to 3. After this, the client runs PIR to fetch the right entry, right sum, which is the second entry in our given example, in our running example. And the client can then reduce M3 by subtracting PIR response from the hint. Note that each query reduces the size of the state. So client has to refetch the state after certain number of queries. So it's not like forever. It's like you have to run. Now we are in a construction where client will run this state fetching scheme in the offline. and then run online queries, and then it has to refresh its state after a certain number of queries, because you cannot use the same subset again and again. Otherwise, server will be able to learn client input. So, okay. So until now, as I just explained the online part of the scheme, right? So online part makes it efficient, and once client has the state, this private state which server is not aware of, then client is perfectly fine running these queries, right? In cheaper queries. But the problem is that how the client fetch this state itself. So for this previous work of Patel et al., which is a work from Google, they introduced a new problem called private batch sum retrieval, or PBSR. In PBSR, the client wants to download sum of random subsets privately. Okay, so however, in their scheme, the Patel et al. Has proposed that the client downloads the entire database in the offline phase, but locally store only the sums of desired subsets. However, as you can imagine, that the result is very big response overhead, and this becomes, if for the offline phase, it essentially just becomes a trivial PIR. Okay, so now I'm going to explain how we improved in our recent work, improved this offline phase. So the key requirement of PBSR is that the server should not be able to learn any information about the subsets, right? So server should not be able to learn which elements are part of the subset, and also which subsets overlap with each other. So one problem here is that, let me just directly go to the solution because of the time. So the way we propose the solution is called select, copy, and permute steps. At a high level, in the select step, the unique elements from the subsets are retrieved. They are not, but they are left on the server. So they, by retrieve, I mean they are selected, but they are not downloaded to the client. Then in the copy step, the client, the elements that are part of multiple subsets. So they could be a same element, since they are random subsets. So there could be multiple elements which are part of the same subset, same element which are part of multiple subsets. So the elements which are part of multiple subsets are copied. For example, if the element 5 here was a part of 2 subsets, so it's copied twice. Note that, however, that after copy step, adjacent entries are likely the copy of same database entry. So we need this final permute to randomly shuffle these entries. So that server will not learn any information. After this, the client can just ask the server to add certain elements together. Note, due to copies, subset overlap information is not leaked. So client server not only doesn't know that which elements go to which subset, but it also doesn't know how these subsets overlap with each other. Okay, so for the fetch step, we just use the latest batch PIR scheme, which allow the server to answer batch of PIR, as I discussed. We directly plug our OnionPIR scheme as a base PIR in the batch PIR construction, which gives us even more efficient protocol. And while the output of this batch PIR is kept on the server, is not downloaded to the client. After that, we perform a copy step using a copy network. A copy network is a special network that replicates input packets from various sources simultaneously. These have been used in multicast networks for some time. Specifically, we have used Beneš's copy network. An example of such network is shown here. The network consists of 8 input, 8 outputs, and all the intermediate nodes are 2x2 switches. Note that this network is, in this network, the first input is replicated twice. Second and third inputs are replicated 3 times. Just a second. So previous work have already provided an efficient algorithm that allow us to configure these networks such that the desired copy requests are always satisfied. So given the copy requests, given the input elements and their copy requests, you can configure the network such that always all the copy requests are satisfied. Okay. So now how can we make that copy network private? Note that the structure is already independent of input. It's the same structure. It's a static network. So all we have to worry about is how we can make these switches private. So in Beneš network, each switch works in one of the four modes. One is called pass-through, flip, or it either copies one of the input on its output terminals. We note that each of the switch can be constructed just using mux gates. So if you have two mux gates, you can put them together, and that can perform all the function of the switch. Previous work have shown that we can create a mux gate just using a single external product. In fact, I think this was a part of TFHE. So here the control bit is encrypted as RGSW ciphertext, and the mux inputs are RLWE ciphertext. And the output of this mux is again RLWE ciphertext. We use these mux gates to privately evaluate the copy network. Specifically, the client sends the configuration bits of the copy network encrypted as RGSW ciphertext, and the server evaluates the network using these bits and his own database as input. Okay. So that's how we do the copy network. For Permute is very similar to actually copy network. So it's almost the same logic, just that each switch only requires a single mux gate. So after copy step, the adjacent entries are likely copy of the same database entry. Why we need even a Permute? So after copy network, only that the adjacent entries are same part of copy of the same element. So this could leak information about the overlap to the server. So we just use the private muxes again to compute a permutation network. This has been actually done in the previous work also, especially in Ring Oram. So this is just an overall approach again, that we first do the pick. Sorry, I mentioned pick here. It's actually select. Then we copy these entries which are part of multiple subsets, and then we randomly permute them, and finally just client asks the server to add them together. So here are some of the results for different database sizes. The results are the sum of, we amortize the offline phase for 500 queries. So after running, each offline phase client can do 500 cheaper online queries, right? First of all, let's look at, so stateful OnionPIR, which is our recent work, has significantly smaller response size because we use this copy network-based scheme and homomorphic encryption in the offline phase. However, the previous works have a very high response overhead just because they download the entire database on the client in the offline phase. However, the trade-off now is that the computation in our scheme is higher, amortized computation, sorry, higher than the Patel et al. Scheme. Again, this is because their offline phase does not require any computation. Still, the stateful OnionPIR reduces the computation of simple stateless PR by large. For example, now it only requires 4.7 minutes to fetch a record from a database with 16 million entries. Recall that it was about 1.8 hours for OnionPIR and SealPIR. Also, the OnionPIR is significantly cheaper in terms of monetary cost. Overall, the monetary cost of stateful OnionPIR is around 10 to 100x cheaper than the previous schemes. Okay. So just a little bit on the future directions. So one of the future direction, which is very interesting to me personally, is how can we combine the benefits of stateful and batch PIR without, the problem there is now that once you try to combine them, the size of the state at the client could increase too much, which makes the protocol not suitable for lightweight clients, which does not have that much extra storage. So how can we do it without blowing up the client state too much? Also, although our PBSR scheme is quite efficient, but still it can be improved. As you can see that the more efficient PBSR scheme will even result in better overall stateful PIR scheme. Also, I think just because we have a stateful, still we should not stop working for stateless PIR. And we should think about how can we improve the computation of stateless PIR even further. Okay, yeah. So that's about it for my talk, and I can take questions now.
I have a few.
Yes, please.
Yes, great talk, by the way. Thank you. I mentioned a few of the questions in the chat. So if you go to slide like 70, I think, around 70-ish.
Okay.
So in the copy network, so I was wondering where the control bits come from. This, yeah, a little bit more. Yep. Yeah, right about here, yeah.
Yeah, so normally, the reason I have this diagram in this way is because normally these switches don't have a configuration bits. You just configure them yourself, that how each of the switch is going to, which mode each of the switch is going to perform. So there are 4 modes. Either they can be passed through, they can flip, or they can copy one of the input on the outputs, right? So in the offline mode, the configuration, you can actually get the configuration and go and just configure the switches, the mode for each of these switches. However, now we are in a client server model. So that's fine if you have the switches, you are going to configure the switches yourself. But now we have this client server model, and clients needs to tell the server that how to configure the switch. So there will be a control bit based on which the client is going to decide, give this hint to the server that what mode he wants the switch to work.
Right. It should depend on the copy values, right? So depending on how many copies of like a V1 you want.
Yeah. So client can do it in the offline, right?
Okay. Right. Okay.
Client knows how many copies he needs, right? Because he's picking the subsets.
Yes. Yes.
So client decides how many copies you need. Client decides what will be the configurations of these switches. So client can generate corresponding bits, control bits for each of the switch throughout the network.
And that's part of the communication cost, right?
Yeah, but this is an offline communication cost. So this amortized over 500 online queries.
Right. So then one more thing was for the permute. So it's a random permutation, right? Maybe it's like slide 75.
It's a controlled permutation. I should not said a word random. Like client decides what kind of permutation.
Right. So there's a, let's say, a seed that controls what permutation that is. So is that seed sent over?
No, even in the permutation, client is going to send the control bits. Again, it will be very similar to copy network.
Right. Okay.
Actually, copy network is built on top of permutation network.
Okay. Okay. Then I guess I can take a look at that. Yeah. Okay. That's it for now. Thank you.
Do we have more questions?
I think everything in the chat has been responded. Does anyone have any more questions, guys? No? Okay, anyway, like the video of the meetup and the slides will be posted on fhe.org. Maybe tomorrow or early next week. A few words before we finish today. Thanks, Mohammed, for this great talk. And thanks everyone for joining. The discussion is always like happening on Discord. If you guys want to like, if you think about any question, like in the few hours, like you can still join on Discord and ask Mohammed and everyone. And also like we are doing a conference with fhe.org. It's going to be hosted part of the Eurocrypt conference in May. It's gonna happen on the 29th of May. And we have like a call for presentation. So if anyone here wants to like present any work really related to homomorphic encryption, you can head over like fhe.org and submit anything. I think we are gonna close the call for presentation on the 7th of March. So there is still some few days to do it.
Okay, yeah, feel free to contact me on Discord, or I have the email in this.
Yeah, you can find all the links like on the fhe.org, the Discord links and the conference links.
Regarding the fhe.org conference, that it's a call for presentations, but also for posters and also for demos. So if you guys have prefer to present like a demo of what you're working on. It can be specific use cases. It can be, compilers, engineering related issues and so on. You're very welcome to submit your work to the FHE.org conference, and we'll be very happy to have this moment where the community can exchange about their experience about instrumenting fully morphic encryption and all kinds of results that we can that we can obtain with this fantastic technology.
Amazing. All right. Thank you, everyone. This was great. Looking forward to the next one. And in the meantime, let's meet up on Discord and continue the conversation.
Thanks, everybody.